Assalamu alaikum. It's day 8 on 13 summer school at LHC Physics. It's today raining, so that's why I put it out the raincoat. Today's similar lectures by Jonas and Frankman and Kristian, Allan, Hans. As I told you in previous day, same lectures today. So enjoy, stay tuned with me. Allah Hafiz.
in the year of 2000 and 2005. and then they switch as well. We are discussing today 3D detectors, low-gain avalanche detectors, monolith active pixels. This is what you have today in your mobile phone. And then we do a so-called depleted monolithic active pixels, or what we also call high-voltage CMOS devices. So these are monolithic active pixels where you can put a bias voltage on the back. And this sounds trivial, but this is absolutely not trivial for English. So these are the novel things that we go through, and then if you want to read a bit further in literature, there are more things. But these are the ones, this is Atlas is using it already, we will use it in phase 2. The low-gain avalanche detector we will use in phase 2. The monolithic active pixel is being used in Ellis as we speak. Installed in the last shutdown on this depleted maps is the one that will be used for sure in Atlas, and there was also a strong push to do it in Atlas. We didn't put it in CMS, and they're not putting in Atlas because for the next upgrade it was just not that sure. So let's go for 3D. Three-dimensional silicon sensors are much more radiation tolerant. And if you just remember what I said about the lifetimes and the time of traveling of the particles, you will understand immediately why. So these three sensors, they work above a fluence of 10 to the 16. 10 to the 16 is where the particles basically only travel 20 micrometers. They work up to, at the moment, up to even 3 to 5 10 to the 16. So where the particles travel in the order of 15 micrometers. So that's why the trapping is the dominant detrimental effect. You don't really care too much on diffusion voltage anymore. The stuff is anymore not really fully depleted. Leakage current, cool it down, cool it, that can help. So you have a long ionization paths that offer no advantage for thick sensors. So this is the sensors that I showed you before. So here you have these strip detectors or pixel detectors. In that area you normally only have pixel detectors because if you get that amount of radiation, you also have a set high occupancy, a high amount of tracks passing the detector that you would violate the 1% occupancy that Kristian told you yesterday. So you need to go to pixel. So here you have this pixel detector, so here you have this standard strip, so this is then, let's say, 300 micrometer thick or 150, what we're using CMS. But the point is 150 micrometer, and then the particles go through, only these particles with the ionizing here participate with the signal. They are too far away, so with the weighting field, they're too far away from this electrode, capacitively they don't really couple, so they're all lost. You only get the signal from the things passing through here, and that is lost. And that signal is then pretty low. In addition, very, very important, and the real reason why we're using them is this thing is thick. And we just discussed yesterday that the voltage that I need to deplete this detector goes squared with the thickness. Meaning, to deplete this detector, I need 800, 900 volts. It has a lot of leakage current, and that means power times current, or voltage times current is power. So the thing gets hot, so you need to cool it. So you want to bring down the voltage, and you want to get a signal of all the different devices. So what do I do now? I go away from this so-called planar concept, and I drill from here. I don't drill, I etch. I drill columns all the way through the detector. So that means I still have the full bulk volume, the full 150 micrometers. The particle all ionizes here. But now, these electrons and these holes, they don't have to travel up here, they just travel horizontally to the columns. That means I can really use the full signal. At the second time, why does the power decrease a lot? The power, the depletion voltage goes from the electrode to the other electrode. So the depletion voltage doesn't form from here to here, it forms from here to here. And that now is only 30 to 50 micrometer thick. So 50 to 150 squared is a lot of power. So I don't need 800 volts. I can deplete it by even after irradiation with 120, 150 volts. For the millennium break. So what you now start to do, you only work with this 10 to 50 micrometer epi layer, so the epitaxy layer is a differently called basic. This is what you basically use on any of your process. So this almost any fab can handle. And then you put the whole CMOS, NMOS electronics on top of it, and then you just have this ionization, but you have no field. You have a little field of this slightly doped N-well and this p-doped bulk, but you know, as we said, this only goes to certain numbers of 1 or 2 micrometer depleted zone. So this is depleted or this is not depleted, and there's no depletion, there's no field. So this poor electron here and this poor hole, they're there, but they don't really know what to do. So they just walk around, and sometimes they end up in the well, some of them end up somewhere else, but the ones who then have in the well, they then see the drift to the end well, and they will be connected at this electrode. And then all here inside this detector, you have the full CMOS. You have a comparator, you have an amplifier, you have certain numbers of electronics that you have in there. So that is A, bad because it takes some time, which we in high energy physics normally do not have, and B, if it takes too much time and this has some trapping inside, all the electrons and the holes, they know exactly what to do, they will be trapped. And we don't get them for the signal. So that doesn't work really for high radiation, not really for small radiation. There's no depletion voltage, it's very thin, it's a very low noise, that's fantastic, very low noise is good. It has a random walk, no drift, and the no drift is the problem. It has an in-cell processing, that's fantastic, and it's very high resolution because these things you can build in the order of 5 micrometer, 10 micrometer. There, the photolithography for the CMOS processes is incredible. This has another problem that here you can only use NMOS electronics, not full CMOS, so you don't have NMOS and PMOS devices, so that limits already your logic a bit. But that is what you have in your mobile camera and in your phone. Everything that is what you can make fantastic pictures. Now,
probably that's going to come through in this talk. I'm going to focus on real-time tracking, so not just track triggering, but real-time tracking. You'll see why I'm saying that. With inner detectors in the midterm for high-energy particle physics. So that's a lot of qualifications. Right? I'm kind of looking at a narrow slice, but you'll see that there's actually quite a bit to talk about just for this sort of realm. One thing that I should specify before I begin is what real-time means. So traditionally, real-time is kind of meant very, very low latency, so on the order of microseconds, below 20 microseconds or say. And that puts this at the level of the hardware trigger. And I'll explain a little bit more about triggering in a moment. What has been going on now at the LHC, and which will carry forward into high Rumi, and then probably to some extent beyond that, is the advent of triggering. A few more qualifications, so I'm not going to touch on anything with the nuance, so just the inner detectors, meaning basically silicon detectors. And I won't try to extrapolate to the FCC, which was the last thing that Frank showed, although a lot of what I'm discussing is kind of, let's say, prototyping the technology that will be available, hopefully, for the FCC. Okay, just to warn you, there's going to potentially be a lot of information in this that I could only sort of skim, but again, I've tried to give the links to stuff, so if you want to look at the documentation and the literature that's there, we can also discuss it offline after the talk. Okay, so first I thought I would try to put the idea of triggering in some context, because this confuses a lot of people outside of particle physics, actually even sometimes within particle physics, but outside of collider physics, but especially the funding agencies who are saying, why are you throwing orders of magnitude of data away? You're building these fancy detectors with all of these channels, and yet you're throwing things away at orders and orders of magnitude. This is a waste of them. And so what we have to explain to them is that this is essentially nature, right? This is imposed on us. This is not our choice. So if we just count up the number of sensors, essentially that we have in the silicon systems, let's say on order 76 million as a ballpark, being read out at 40 megahertz, that would give you a petabyte of data per second coming out of the detector. And imagine trying to store a petabyte per second, but it's completely impossible. And the reason why we can't store that is just because the interaction rate of uninteresting physics, so like minimum bias, soft collisions, kind of like the pileup events, that's all the way up here in terms of the cross-section. And this is showing cross-sections versus collider energy, so this essentially is production rate. And this scales from something like CDF, so 2 TeV center of mass, to the LHC, and then something like this would be the FCC. You can see how these things grow. So the total cross-section, which corresponds to very old physics, right, that we're not interested in anymore, is the background. That is actually growing, and it's all the way up here. You have to look 10 orders of magnitude all the way down here to find something like the Higgs cross-section. And for our detectors, we don't want to take all of this, right? We want to drill down to something like that. So we have to be intelligent about how to select events out of the soup in order to get to the interesting new physics that we want to try to measure. Of course, the main reason why we're exploring a hardware trigger at CMS is because of pileup, right? So this picture looks pretty nasty in the top corner, and if we can at least find these tracks and their longitudinal impact parameter, we can try to reject them on that basis and cut down on the pileup. And that improves our overall efficiency and resolution for objects that go into the trigger. And to your point, this is, to your question, this is, for instance, the efficiency of a muon trigger, showing you the difference where you have level 1 tracking, which is the black here. So here we're looking at a trigger path where it's muons, 20 muon trigger, for instance. And you see the efficiency turns on exactly at 20. It's very sharp and nice, and it plateaus immediately at something like 97% in terms of efficiency. If we didn't have that level 1 trigger, we would have curves that look like this, with a very slow turn on for the same selection, right? Even after the 20 TeV, it's still turning on, it's still not fully efficient, and eventually it plateaus at somewhere even below that 97%. Okay, as I mentioned yesterday, the CMS track trigger is based on the stubs that are coming from the PT modules. This very intelligent detector design allows us to immediately reduce data rates coming out of the detector by a factor of 10. And without this, we wouldn't be able to do a track trigger. This is the reason why Atlas ultimately couldn't do a track trigger, is because they don't have something like a PT module. So even with that factor of 10, you still end up with 15,000 stubs per loop processor. So every 25 nanoseconds, you have 15,000 stubs that you have to perform tracking them. And you have to do that in CMS on a 4 microsecond latency budget. So 4 microseconds to do full tracking of 15,000 stubs. The algorithm that we will use, or that is the current baseline in CMS, is somewhat of a hybrid. So it has what we call a tracklet stage that does the pattern recognition, followed by a common filter for the track fitting that extracts the parameters, and I'll talk about this in a few slides. Okay, so in terms of CMS, level 1 has to confront 2 real problems. So as I just mentioned, there's pattern recognition, and pattern recognition means associating those hits that should be considered part of a single trajectory. So if you just take all of those 15,000 stubs, right, you wouldn't know where to begin. You need to sort of start to associate them as saying, this one belongs with this one in the next layer, and then this one. And then after you have a full collection of hits, you can do the tracking to extract the PT or the impact parameter, for instance. And so this pattern recognition stage is also known as track finding, and essentially that's just associated, again, hits with track candidates. After that, you do the track fitting, and that's the efficient extraction of track parameters from many candidates. And these two steps aren't necessarily as independent as I've made them out to be here. So track fitting, in some sense, performs some residual pattern recognition as well.
That none of them have a 3 sigma effect, right? All of them are within 3 sigma, 1 minus that. And that is the probability that one of them is within 3 sigma to the power of 100. I have a computer, I can calculate this, and that is 1 minus 0.76, that's 24%. Now, the probability of claiming a full discovery of a quarter, that is far too risky. I'm not going to do that. And so this is what these p-values are about. In a way, you can interpret the p-values as the probability that, under the assumption there's nothing new, you make a fool of yourself by claiming there is something new. That's what basically the p-values represent. And then you have to take into account whether you look only in one single place or whether you look at many different places before you do this quantity. But the more often you roll the die, the more likely you get a specific result, right? The more often you do an experiment or look at something, the more likely you are to get a 3 sigma or 4 sigma effect. It's really important. I just, because it is important, I calculated a few more values for you. So to have, this is the first one we started off with, we have one 3 sigma effect of one measurement, that is this 1 minus 99.73%, so it's 0.27%, and 10 is 2.7, in 100 it's 24%, and if you do 1,000 measurements, then it's 93%. So you can be guaranteed that somewhere in our field there's a bogus 3 sigma effect. It's really 3 sigma away, but it doesn't signify anything new, because surely we are doing more than 1,000 measurements in our field, right? There will be one or two. And that's why when we see 3 sigma effects, we don't dismiss it. We say it's an interesting observation, it's interesting, it's a hint, it's an indication, but we don't get overexcited, because the large number of measurements we make implies that we'll see these come and go occasionally. And I find it a bit mind-boggling, it has, because the same result means something quite different when you had, if you look only at one single measurement, one single histogram bin, and you decided that from the start to only look into this one single histogram bin, and you see a 3 sigma variation there, or whether you also looked at the other 99 bins in the histogram, or the other 99 measurements. I find that a bit mind-boggling, so your result that you look at means something different if you look at other things as well, or if you haven't. In particle physics, we usually take 5 sigma as the threshold for discovery. That's of course somewhat arbitrary, but 5 sigma is pretty good, pretty safe. So having a 5 sigma effect in 100 measurements, the probability of that is tiny. Nobody really knows. But there's infinite entries, and in my experiment, I take some number of measurements. In the previous one was 101. Here I take 10, and I make a measurement of the mean and I get also get an uncertainty on the measurement on the width of the distribution. I take another measurement of the mean and the width, etc. So these means, if I put them in a histogram, they will fluctuate a little. They give the distribution, and it's the width of this distribution that I mean when I talk about the uncertainty on the mean. So in the previous one, it would be, okay, I took 101 data points. If I repeated this many times, there would also a jitter on the mean I get, and the width of that jitter, that will be this number. So that's what I mean, that's certainly on the mean. Any questions on that bit? Because we're changing a topic now. We're changing it to...
By the way, somebody yesterday asked me what was the name of the package that you use to draw the random distribution and then it generates the data. You arbitrarily draw the...
That is a student of mine wrote this for me. The interface is bouquet, so that is the thing that allows you to draw. And yeah, and in the recent version it stopped drawing properly, so you saw that it sort of stopped drawing, the lines were interrupted. So I'm trying to fix that. But it's not a commercially available package. It's a PhD student of mine who did this for me. Okay. So I'm happy to share the code.
Okay. I have given some exercises to, let's say, draw as a sign distribution, and that, of course, that's in root, but that seems more.
It's fun. It's fun. Yes, you can draw anything arbitrary. It's quite cool. Yeah. So. So Daniel Saunders, remember the name? He's a very bright guy. Daniel Saunders is the guy, very smart. But also now in industry, programming games or something like that. Anyway, so after this, this is what I wanted a little bit of an intermezzo before I change topic. And I'm going to rush through this a little bit just to make sure we have time at the end for the bit that I find important. I'm going to introduce you to two further distributions. So we have the Gaussian, and I hope I convinced you why the Gaussian, and why the Gaussian is so very, very important, and it pops up everywhere. But there are two more that really pop up a lot in particle physics. The first one, that actually is not that frequent, but it's the introduction that we need for the second one. It's a binomial. And the idea behind a binomial is you have a fixed number of trials. So you try something out a fixed number of times, so you toss a coin maybe 5 times or something like that. And you have 2 possible outcomes for a coin that would be heads or tails. You can also use it for dice, but the die has 6 possible outcomes, you have to reduce it to 2. So you could say, I roll a die 5 times and I record whether it's an even or an odd number. Or if it's number 6 or not the number 6. That also is a completely valid way of doing it. Traditionally, they're called success and failure. It's a bit judgmental maybe, but that's what they usually call. And there's many board games where, for example, if 6 is required to progress, then a 6 would be a success and everything else would be a failure. The probability for success in a single try is p. In my example, with a board game where I need a 6, it's 1/6, because I have a 6-sided die. And then the question that this answers is what is the probability to get r successes, and then consequently n minus r failures, when I try n times. So if I roll my die 5 times, how likely am I to get 1, 2, 3, 4, 5 6s, or 0 6s? And yes, here's the whiteboard. So I will derive this for you, but in order to cut corners a little bit and save a bit of time, I'm just going to give you the answer. And I'm going to talk you through the answer at least a little bit. So if this is my probability, my binomial, and this is the number of successes, the number of trials, and the probability for success in each trial. So if I try r times, and I want r successes, the probability of success with 1 try is p, 2 tries, the 2 successes is p times p, 3 successes is p times p, etc. So that gives me p to the power of r. And then say, okay, after I've had my R successes, I want n minus R failures. The probability of a failure is 1 minus p. And the probability of n minus R failures is then 1 minus p to the power of n minus R. But that would be the case for an ordered outcome. First R successes, then n minus R failures. I don't care in which order I get my 6s and non-6s or whatever. So I have to multiply this by the number of ways there are to pick R things out of n, R successes out of n trials. So basically the number of ways in which I can order these. And that is represented by the symbol, and this means n factorial divided by R factorial times n minus R factorial. So that's a binomial distribution. Not properly derived, but I hope you find it sensible, at least, and plausible. And this is how it looks like for different values. So I took P as 30%. Why not? And I plotted it for different numbers of trials. So for 0 trials, obviously I can't succeed, right? There's no chance. So the probability that I get 0 successes is 100%. And the probability that I get anything else is 0. For 1 trial, also more or less by definition, the probability to get 1 success is 30%, and 1 failure, and 0 successes is 70%, that's 1 failure. And then it moves on a little bit, becomes a bit more complicated. And then this is now for 10 trials, 100. Do you see what's happening there, by the way? What this is turning into? It's turning into a Gaussian, obviously. Like everything does, really add enough data together. So the Poisson, the binomial distribution will become a Gaussian eventually if you have enough trials. And the expectation value is just n times p. That makes a lot of sense. If my probability of success is p, then if I try n times, I expect n times p successes on average. And then there's also a standard deviation that has a square n factor in there, always lots of square n's. And one thing I think is sort of nice and plausible about this expression is that it is symmetric in success and failure. Because if I have 1 success, it means I don't have 1 failure, and the other way around. So this is the probability of success, this is the probability of failure, it's symmetric in those two.
the W and the Z. And this picture shows most of them at a prize-giving ceremony. Peter Higgs didn't attend. You can see him in the bottom left-hand corner. Maybe he's still working on his theory. And unfortunately, as time has gone by, many of these founders are no longer with us, but a couple of them are, François Anglaire and Carl Hagen. Peter Higgs himself passed away earlier this year. So as I said, the story started in 1964. The first paper on the subject of giving masses to gauge vector bosons was actually written by Anglaire and Brout. And this was followed soon afterwards by 2 papers by Peter Higgs. Peter Higgs was unaware of their earlier work. And in fact, of all the people on the previous slide, Higgs was the only one who explicitly mentioned the existence of a massive scalar boson. And this proved important subsequently as being a key experimental signature of these ideas that had been proposed for giving masses to vector bosons. I'm not sure if you can read it out in the bottom right-hand corner of the slide. I mentioned a later paper by Migdal and Bolyakov who at the time were students in Moscow, and a little bit later than the others, but completely independently, they invented all the ideas about spontaneous symmetry breakdown and mass generation. And at the time, their professors were very skeptical, and as a result, the paper was delayed in publication. But I think they deserve some credit for coming up with these ideas independently. So on this slide here, I'm trying to illustrate in this picture the idea of spontaneous symmetry breaking and the contributions of the various different founders of the subject. So the picture in the middle illustrates the shape of the effective potential, the energy level, which they postulated. So you have some field phi, which in the simple model has real and imaginary components. And the energy function, the potential, has a rotational U1 symmetry. Now the shape of the potential is such that a zero value for the field is not a stable configuration. The field will always try to go to a minimum of the potential. But you'll see that there is a circular set of equivalent minima of the potential. Now what Nambu, the guy on the left here, pointed out was that when the theory settled to its minimum energy configuration, there would be a massless degree of freedom corresponding to going around the bottom of the potential. And that's what we call the Nambu-Goldstone boson. Now what Henri Braut, Higgs, and Garanik, Hegel, and Kibble did later on in 1964 was they postulated, in addition to the scalar field phi, a vector field, a simple example, rather like a photon. And they pointed out that the vector field would combine with Nambu's massless scalar field to produce a massive vector boson. Now, the observation that Peter Higgs made in his paper, but the other people did not make in their paper, was that in addition to a massive vector boson, there will be a degree of freedom corresponding to going up and down the potential in the radial direction. And in quantum field theory, going up and down the potential corresponds to the existence of a massive scalar particle, the Higgs boson. So I'm sure that you've read it before, but let's just recall that in the standard model, you have this SU3 gauge group for the strong interactions, you have SU2 cross U1 for the weak interactions, and here I've listed the leptons and the quarks, and their representations under this composite gauge group. So, these are the quarks and triplets of SU3, left-handed leptons of doublets of SU2, and so on. So the Lagrangian corresponding to this theory can be written on the t-shirt, as you can see here. So it's got 4 lines. The first line describes the gauge interactions. So it basically encapsulates Maxwell's equations and generalizations to these other gauge bosons. The second line describes how these interactions work on the particles of matter, the matter fermions. So think photoelectric effect. And the 2 bottom lines involve the Higgs boson fine. So there's a set of interactions between the Higgs boson and fermions, so-called Yukawa interactions. And at the bottom we have the Higgs potential V, which I introduced earlier on, and the Higgs kinetic term. So the top two lines have been tested before the LHC at the fermion level or better. And of course the LHC is now testing the two bottom lines. And I'll describe where we are with those probes of the interaction of the Higgs boson shortly. So the standard model, as I wrote it on the previous slide, contains many parameters. It contains three gauge couplings, the SU3, SU2, and E1 gauge group. There's also the CP violating phase that I won't go into. Those Yukawa interactions, they have many parameters. They need to describe the charged lepton masses, the quark masses, and the mixing between the quarks, which gives us the Karlsruhe, Scala angles in phase. And then the Higgs sector of the theory, which is contained down here, the Higgs potential, has two parameters which I've already introduced. There's a mass parameter mu and a quartic interaction parameter none. So there's a grand total of 19 parameters here, so I don't think anybody believes that the standard model is a fundamental theory, and we would like eventually to unify the fundamental interactions. We would like to understand why these Yukawa interactions have the different values that they do, and we would like to understand the Higgs sector at a more fundamental level. But I'll be discussing some of those issues later in my lectures. But what I'd like to do now is to look a little more closely at the standard model of Lagrangian, and discuss in more details how the whole thing works. So in this green box here, we have the gauge interactions of the quarks and leptons. So here we've separated the quarks and leptons out into the left-handed and right-handed components, and they interact with vector bosons through covariant derivatives denoted here by capital D. And this is the part of the theory that has been verified better than percent accuracy before the LHC. And in the red box, we have the Higgs sector, for which there would be no direct evidence until the discovery of the Higgs boson announced on July 4th, 2012. You can see here how the Higgs couples two left-handed and right-handed quarks. I discussed the motivations for the Higgs boson, some of the theory behind it, and what we know experimentally about it and its properties. So, the discovery of the Higgs boson was the discovery of the last particle in the standard model. And if you are a nasty funding agency, you might say, well, okay, great, you've got a theory which describes all the visible matter in the universe. Thank you very much. You can all go home now, and we'll give the money to something else. Well, needless to say, I would disagree with that. And my disagreement is described in this quotation from a poem by T.S. Eliot. To make an end is to make a beginning. The end is where we start from. So the way I interpret this is by completing our knowledge of all the particles in the standard model, they can end to one phase of particle physics. But that is where we start from to continue to look for physics beyond the standard model. And as I'll discuss in this lecture, there's plenty of reasons to think there must be physics beyond the standard model. In particular, the Higgs itself is extremely puzzling. And I'll discuss at least some of the ideas concerning possible scenarios of physics beyond the standard model. This is sort of my summary of where I think we are. So, in the first lecture I discussed how we progressed from speculation about spontaneous symmetry breaking to hypothesis as to how this could happen, a theory, a standard model, research that Higgs boson, we discovered it, and now it's a building block of our understanding of nature. And now may be the time to repeat the cycle by discussing speculations about what lies beyond, and hopefully going through this whole procedure again. So why am I so convinced that there must be physics beyond the standard model? So this time I take my inspiration from this old movie featuring James Bond. For him, the world was not enough, but I paraphrase that as saying the standard model is not enough. And I changed the hero of the movie. I also changed the villain of the movie, and in reference to James Bond, I give you 007 reasons for thinking that there has to be physics beyond the standard model. So one of them is in fact already mentioned in the Q&A at the end of the first lecture, namely the fact that when you calculate the properties of a vacuum in the standard model, you find that it appears to be unstable. So is it something that we believe, or do we believe that there's some new physics which is going to come in to stabilize the vacuum? Then I emphasize the fact that the standard model is a theory of the visible matter in the universe. But astrophysicists tell us that there is a whole lot more invisible dark matter. And what is that? There's no candidate for that in the standard model. So I won't discuss dark matter in this lecture, but I will in subsequent lectures. I've been talking about matter, but what is the origin of matter? Why is there matter and not just radiation or an equal mixture of matter and antimatter? I'll discuss the facts that the Higgs travels to particles proportional to their masses. Of course, we know there's an enormous ratio between the mass, for example, of the top quark and the electron in motivations. One was that, as I've already advertised, supersymmetry could stabilize the electric vacuum. Another one is that in a supersymmetric theory, you can calculate the mass of the Higgs boson, including quantum corrections. And the prediction is that it should weigh less than about 130 GeV, which it does. And in such a supersymmetric Higgs theory, we predict that the couplings of the Higgs should be equal to the standard model values to within a few percent, which seems to be the case. So this is all great. So these are new motivations, in addition to the argument for naturalness, which I mentioned on the previous slide. The fact that supersymmetry helps you construct grand unified theories, as I will discuss in a moment. The fact that supersymmetry plays a key role in string theory, which I don't think I may have time to discuss in this lecture. the fact that the lightest supersymmetric particle can provide dark matter, which I will discuss in a future lecture, and the possibility that if the enormous magnetic moment of the muon differs from the standard model value, then that could be explained by supersymmetry, which I will also discuss later. So lots of motivations for thinking about supersymmetry. So in supersymmetry, the particles of the standard model are each accompanied by partner particles, which have similar electric charges, strong interactions, but they differ in spin by half a unit. So for example, quarks have spin 0, as opposed to quarks with spin 1/2, and also the supersymmetric partners of the photon, muon, Z, and W, and Higgs also have spin 1/2. Now, amongst all these supersymmetric particles, one of them has to be the lightest. And in many supersymmetric extensions of the standard model, that lightest supersymmetric particle is stable and could provide the dark matter. So, I'll discuss this in more detail in a future lecture. But there are several candidates within supersymmetry to be that dark matter particle, including the supersymmetric particles of the Higgs, photon, and the Z boson. So I already advertised that in supersymmetry you can calculate the mass of the Higgs boson, and it turns out to be below 130 GeV in agreement with the experiment. So this is something that we realized around 1990, 1991, and here is a prediction from those days of how heavy the Higgs boson might be as a function of the parameters of the model. And you see that the maximum value is 125 GeV, which we all know now is indeed the mass of the Higgs boson. So I also mentioned that supersymmetry could help with grand unification. So this is the idea that the various different gauge groups in the standard model could be unified in some simple group which would come manifest at high energies. And in this simple group, all gauge couplings would have to be equal. So of course the couplings we measure at low energies are not equal. But you can calculate how they change as a function of energy. And I won't go through the details of this calculation, but these parameters here tell you how the couplings change. Supersymmetry will also change, but they change in a different way from in the standard model because you've got additional particles which contribute to the variation, the running of the fundamental couplings. For example, QCD coupling is still asymptotically free, that's -11, but now it becomes -9. Because we have supersymmetric partners of quarks, squarks, incremental calculation.
Dried out tears of sorrow. I will try to fit in my time because I'm actually having a constraint, given the fact also that I'm starting about 14 minutes late. So I hope I will be done as I'm supposed to be done within 15 minutes and not more.
No, you can have already the 15 minutes if we are biased, so I mean that should cover that.
No, I understand it, but my problem is I have my own constraints. Very briefly, so I'm working on the CMS experiment, which is one of the experiments at the Large Hadron Collider. I'm sure you're very well aware of already all this picture as well as of Large Hadron Collider, but still I will mention, so this is the largest collider to date in the world, which exists on the border between France and, I'm trying to see if you can see my mouse. You don't see my mouse, I guess.
Unfortunately not.
Just a second, something. I kind of see. So why is that? Between France and Switzerland, so I marked here you can see it's from CERN, you can see sometimes Mont Blanc when the sky is clear, and we are very close to Geneva Airport. And this is how things look from above. So basically this all is located pretty much in very residential parts of the countries. But of course everything is underground, so it's 100 meters underground. The whole circumference of the tunnel is about 27 kilometers, and those 4 main experiments are located underground at this level. And the CMS, together with Atlas, are what we call general purpose detectors, which are designed specifically to study a broad range of physics topics, starting from measurements as well as searches and so on. While we have 2 other types of detectors, which is LHC and Ellis, which are specifically targeting some processes that they are sensitive to. So in particular, LHC being to study the processes with big quarks or big mesons, and Alice is to study heavy ions. So you know that we are collecting now data at central mass energy 30 TeV, and the collision rate is very high. So, just to give you an idea, maybe you've seen also this short video, but this is how collisions take place at the LHC, and in particular the collisions happen in the center of the detectors, so at this 25 megahertz frequency. And the purpose of these detectors are, of course, to really detect all the particles that are produced in the collisions, and then identify what are those particles, and most importantly, then identify where these particles come from. Because in most of the cases, we observe the particles that are products of the particles, intermediate particles, which are produced in these collisions and decay instantly. Like when I say instantly, it's not even in a matter of a second, but it's very, very small fraction of seconds. Yeah, so we cannot really detect particles which live so short, but we can only detect their decay products. And by precisely understanding the properties of these decay products, reconstructing them and so on, we are able to infer which particles were produced in the collisions. So because of that, it's super important for us to have very powerful detectors which allow us to perform very precise measurements of the physics quantities of these decay particles. Yeah? So we measure basic physics quantities, energy, momenta, charge, trajectory, and so on. And using this, we can predict what happened at the collisions. So basically, how CMS detector is built in order to be sensitive to all sorts of different particles that are produced or decay products that are produced in these collisions. So this is on the left. You can see here basically the YZ and YX view of the CMS detector. So you know it's a cylindrical shape. I will not go into detail, but most important I want to draw your attention is the diagram on the right, which shows how different types of particles propagate through a CMS detector. And this is just this slice in the transverse plane of the CMS detector. So you basically see here all layers of the detector. So the detector is built of what we call sub-detectors, or different components, which each of them has its own purpose. Basically, each of them is designed in order to identify some specific particles. And as I said, we identify the stable part, basically the decay products, which are pretty much stable in the frame of the detector. Yeah. So particles which do not decay anymore to the level that they basically can be detected within the detector. So what are those type of particles? So here, these are these are listed on the top of this top corner of the slide. So basically, we can group them into 5 types of particles. So whatever we identify in the detector, this is neon, electron, photon, charged hadron, and neutral hadron. Okay, so, and the detector is built in order to be sensitive to each of these types of particles sequentially. So, first we have inside the tracker, which I think you already heard some lectures about it, or are going to hear more, which are to identify tracks of charged particles. Then we have calorimeter, electromagnetic, to identify particles that interact electromagnetically, and this is obviously majorly electron and photon. And then that's followed by the hadron calorimeter, which is to identify particles that interact hadronically, charged hadrons, neutral hadrons, and at the end we have a detector for muons. Because muons are not stable particles, as we know, they decay, but they actually are stable from the point of view of CMS, because they go through the whole CMS and decay afterwards. Yeah, so they do not interact or interact minimally to the inner parts of the calorimetric parts, and then they are measured by muon system. So calorimeters are actually the detectors that try to measure energy of incident particles. And just to remind you, so calor is a Latin word for heat, and meter is, we all know it's a meter English word, so to measure. And that's what calorimeters do. They try to measure energy of the incident particles, and in particular what's important is that they try to do this measurement in a destructive way. What it means is that the particle eventually has to be kind of destroyed, and that's how we are able to have a full information of the initial energy of the particle, and once they fully kind of get destructed. Yeah, and that information is possible to be obtained using the calorimeters, and we have 2 types of calorimeters, as I already mentioned. This is electromagnetic calorimeter targeting to electrons and photons, and hadron calorimeter targeting to hadrons. So the palm, and it's super heavy. Like if you will visit CERN, we have in some exhibition place one of the crystals. Next to it is also real, just simple plastic of the same dimensions and shape. So they look identical, but when you can hold them, and this crystal one is super heavy. So it's lead, but somehow it's made transparent so that photons can propagate and produces and electrons as well, of course, and give us a good signal, this high resolution. At the end, you see here APDs that are attached, avalanche photodiodes, to read out this signal. And I will skip these details of each component of ECAL, barrel, end cap, threshold. These are just some of the parameters. And here you can see how these crystals were made quite some time ago, 20 probably years ago or so. And of course then they need to be all measured individually and parameterized, because they are not, even though of course technologies are developed and try to make very similar crystals, there's always some differences, and we need to make sure that they are more or less uniform. So we have to have characterization of each of them and apply necessary corrections. So now once we have detectors, what's the next step? Is to try to see how they perform. So ideal situation is usually at the test beams when we have no magnetic field, no material in front of the detector that we want to test, or part of the detector, very, very minimal radiation. And so we try to check how this detector performs, what the resolution we measure, and we get very nice performance, whatever is our target, so we are all happy. But of course, when it comes to real experiment, let's say it's somewhat far from the ideal case. So because we have many factors that affect our energy resolution. So, for example, light yield can vary in the detector. So this can vary because of the dependence on the temperature. It can vary because of, for example, the transparency of the crystal or the scintillators that are significantly affected because of by the radiation. And depends on what type of material we're dealing with. Sometimes it depends on the dose of radiation or dose rate, and so on. Now, we also have an effect on the photodetectors itself, so they can change, the gain of the photodetectors can change with the temperature, so we have to have control temperature wherever we have photodetectors. So we also could have some noise effects, some discharges in the photodetectors, or some other effects on the cathode, for example, in PMTs that was appearing in the HF in RAN 1. So in order for our detectors to perform reliably, we need to basically develop many methods to monitor the detectors, to calibrate the response so that all these variations are corrected. Whenever, for example, radiation damages makes the crystals to darken and darken, the signal that we read out is changing, yeah? But it is still produced by the same type of photon, for example, coming from Higgs. So we need to add additional correction with time so that this effect is removed and we can still reconstruct original energy of the photon produced from Higgs or electron produced from W, for example.